Hello everyone, today we will learn about the graph of sine and cosine functions. Trigonometric functions are a new class of fundamental elementary functions that we learn. According to the method of function research, after learning the definition of trigonometric functions, what problem should we study next? Everyone is right, we should continue to study the graphs and properties of trigonometric functions. Please think about our previous approach to studying the graphs and properties of exponential and logarithmic functions. We first clarify the definition of the function, then use the definition to study the graph of the function, and then use the graph of the function to study its properties. We have already learned the definition of trigonometric functions before, so next we will study the graph of trigonometric functions. May I ask everyone, what is the basic method for drawing a new function graph? Yes, the basic method for drawing a new function graph is the point drawing method. So, according to the definition of trigonometric functions, is it necessary to plot the function graph of sine functions over the entire domain? Which interval should I choose? According to the definition of trigonometric functions, any point on a unit circle that rotates once on the circumference returns to its original position, that is, sine alpha plus 2k pi equals sine alpha. Similarly, cosine alpha plus 2k pi is equal to cosine alpha, where k is an integer. So we can first draw the graph of the sine function in the closed interval 0 to pi, and then draw the graph of the sine function in the domain R. So now let's first study together how to draw a graph of a sine function. Since point drawing is the basic method for drawing function graphs, what points do you want to take for sine functions and how do you draw point graphs? Some students say that they can randomly take some values for the independent variable on the closed interval 0 to 2 pi, then use a calculator to calculate the function value, and then draw a line of points on the plane Cartesian coordinate system. Do you think this is feasible for making a graph? This diagram should be able to roughly depict the shape of a sine function in the closed interval of 0 to 2 pi. However, for sine functions, both false radians and sine values will result in some irrational numbers. If a calculator is used for drawing, it is clearly not precise enough and does not utilize the definition of trigonometric functions. So, can you find a more accurate method that utilizes the definition of trigonometric functions? Okay, let's think further. To draw a graph of a function, the first step is to accurately draw a point on the graph. So for a sine function, if we take any value x0 in the closed interval 0 to 2 pi, how can we use the unit element to determine the sine function value sine x0 and accurately draw points t, x0, and sine x0? Please refer to the picture and draw a unit circle with the origin as the center in a Cartesian coordinate system. The intersection point between the unit circle and the positive half-axis of the x-axis is a 1, 0. On the unit circle, rotate point A around point O by x0 radians to point B. According to the definition of radians, the absolute value of alpha radians is equal to the arc length L to the radius r, with a unit radius of 1 within the circle. So at this point, x0 is both the size of angle OB and the length of arc AB, and according to the definition of the sine function, the vertical axis y0 of point B is sine x0. So we can draw points with x0 as the horizontal axis and y0 as the vertical axis to obtain a point T on the function graph, x0. Sine x0. Now that we have learned to draw a point on the graph of a sine function, can you come up with a plan to draw the graph of a sine function in the closed interval of 0 to 2 pi? There are many different solutions for this problem, and now we will analyze them one by one. Some students say that they can take some values of the horizontal axis within the closed interval of 0 to 2 pi, and then draw points one by one according to the above method, and connect them with smooth curves. However, please note that if we take arbitrary values for x0, it may result in rational or irrational numbers, making it difficult to accurately locate on the x-axis. According to the definition of radians, the value of x0 is the length of arc AB, making it difficult to translate. So there are certain difficulties in locating the middle of the x0 radian angle on the unit circle. So some students suggested that we should not arbitrarily take the value of SO. We can take values like 1, 2, 3 radians, etc., draw a function graph using the above method. These radians, such as 1, 2, and 3, can indeed be accurately located on the x-axis, but when trying to locate the final edge of these radians on the unit circle, the above problem still exists. We still have difficulty accurately locating the position of point B. Some students have suggested that we should take these familiar special angles, such as 1/6 of pi, 1/4 of pi, 1/3 of pi, and so on. These special angles within the closed interval of 0 to 2 pi are indeed familiar to everyone and easy to locate on the x-axis, but how to determine the position of point B on the unit circle? What special angles should we take? How to take special angles to make the drawing both simple and accurate? Okay, a classmate has proposed an improvement plan. We can take equal points within the closed interval of 0 to 2 pi. This way of drawing is both simple and accurate. Please take a look at the picture together. First, we can divide the closed interval from 0 to 2 pi on the x-axis into 12 equal parts, so that the value of x0 is 0, 6 parts pi, 3 parts pi, and up to 2 pi, which are special angles. The intersection point between the end edge of the corresponding angle and the unit circle also divides the circumference into 12 equal parts. We can draw points t, x0, and sine x0 in sequence according to the above method. Everyone, now please join me in creating a graph of a sine function in the closed interval of 0 to 2 pi. Firstly, we divide the closed interval from 0 to 2 pi on the x-axis into 4 equal parts, and then divide each subinterval into 3 equal parts. Thus, the closed interval from 0 to 2 pi on the x-axis was divided into 12 equal parts. Then make a unit circle with the coordinate origin as the center. The middle edges of these special corners also divide the circumference into 12 equal parts. In this way, we obtain the intersection points between the final edges of these special angles within 0 to 2 pi and the unit circle. Now let's describe some points. First, sine 0 equals to 0, so the graph of the sine function passes through point 0, 0. Let's take a look at 1/6 of pi again. The vertical coordinate of the intersection point between the end edge of the angle and the unit circle is 6/10 of pi. So we can plot the point with 1/6 of pi as the horizontal axis and the external value of this point as the vertical axis, thus obtaining the point of 1/6 of pi, since 1/6 of pi. Let's take another look at 1/3 pi. The vertical coordinate of the intersection point between the end edge of the angle and the unit circle is 1/3 pi of sine. So we take 1/3 of pi as the horizontal axis and the external value of this point as the vertical axis to plot the point, and we can obtain 1/3 of pi for point and sine 1/3 of pi. By analogy, using the same method, we can sequentially determine the positions of all corresponding points on the closed interval 0 to 2 pi. Then, by connecting these points with a smooth curve, we obtain the graph of the sine function in the closed interval of 0 to 2 pi. This is the graph of a sine function in the closed interval 0 to 2 pi, which is a continuous and smooth curve. So, based on the graph of y equals to sine and x in the closed interval 0 to 2 pi, can you imagine the graph of these functions in the domain R? What is your basis? Please draw a graph of the function. According to Formula 1, we know that sine alpha plus 2k pi is equal to sine alpha, where k is an integer. Therefore, the function y equals to sine x in every closed interval such as 2k pi to 2 times k1 pi, where k is a non-zero integer. Its graph should be exactly the same as the shape of the sine function in the closed interval 0 to 2 pi. Thus, we can continuously shift the graph of the sine function in the closed interval from 0 to 2 pi to the left and right by 2 pi units, and obtain the graph of the sine function in the domain R. This is the graph of the sine function on the domain R. The graph of a sine function is called a sine curve, which is a continuous smooth curve with undulating waves. The study of functions often plays a particularly important role in quickly and accurately drawing their diagrams. So, can you draw a diagram of the graph of the function y equals to sine x in the closed interval 0 to 2 pi? What key points should be grasped when determining the shape of an image? Please observe the graph of the sine function in the closed interval of 0 to 2 pi. We can see that the key points here are the maximum point, minimum point, and the intersection of the curve with the x-axis. Because with these points, the shape of the curve can be determined, so we will use these points as key points to draw a plot. Their coordinates are 0, 0, half pi, 1, pi, 0, 3/2 of pi, 1, and 2 pi, 0. Generally, when precision is not required, we can first identify these 5 key points and then connect them with smooth curves. This method is very simple and practical, and it is called the 5-point method. Now we are able to create a graph of sine function. Can you create a graph of cosine function? Some students say, let's use the definition of cosine function and draw points with the help of unit circles, just like before. Please think about it. If we still use the previous method and the horizontal axis of point B on the unit circle is cosine x0, is it still easy to use this coordinate when we want to draw a cosine function with the horizontal axis of point B as the vertical axis of point P? Obviously, it is no longer easy to use. Can we find any simpler way? From the definition of trigonometric functions, we know that sine function and cosine function are a pair of closely related functions. The induction formula already indicates that cosine function and sine function can vary from each other. Therefore, can you obtain the cosine function image through the image transformation method based on the obtained sine function image? Someone immediately thought of this induction formula, y equals to cosine x equals to sine half pi minus x. However, please note that in this formula, x is preceded by a negative sign, and half pi also involves translation, so the image changes are quite complex and not easy to operate. Do we have a more concise induction formula that can be used? Someone thought of this derivative formula, cosine x equals to sine x plus 2 pi, which is indeed much simpler. When we were in junior high school, we learned about image translation. We know that by shifting the sine function image to the left by a unit length of half pi, we can obtain the cosine function image. Please refer to the picture. We can shift all the points on the sine function graph by half pi units to the left. For example, translating 0, 0 points to negative half pi, 0, translating half pi, 1 to 0, 1, translating pi, 0 to half pi, 0, and so on. Thus, by shifting each point on the sine curve by a unit of half pi to the left, the graph of the cosine function on the domain R is obtained. The graph of the cosine function on the domain R is called a cosine curve, which is a wavy curve with the same shape as the sine curve. We all know that curves are composed of points. Can you use the coordinates of points to explain this translation transformation? Let's analyze together. Let any point on the graph of the function y equals to sine x be mn, that is, sine m equals to n. When the function y equals to sine x plus 2 pi is equal to m, that is, when x equals to m minus half pi, the value of the function is also n. So there is a corresponding point on the graph of the function y equals to since x plus 2 parts pi, with its coordinates being m minus half pi n, then we can see that by translating point m to pi of point m minus half pi, n, obviously, this point has been shifted to the left by a unit of half pi. At the same time, we arbitrarily take a point on the sine function graph, so it means that all points on the sine function have shifted to the left by a unit of half pi. So we further explained this translation transformation using the coordinates of the points. How can we make a simplified diagram of the cosine function, similar to the 5-point method for creating a sine function image? To think about this issue, we should first consider which interval to choose for studying this problem is more reasonable. So, according to the definition of the cosine function, we can know that we still need to take an interval of length to pi. Based on the characteristics of the cosine curve, it is symmetric about the y-axis, so we may as well take an interval that is symmetric about the y-axis. This way, it is more reasonable to take the closed interval from negative pi to pi. So, please observe the graph of the cosine function on the closed interval negative pi to pi. Which points should we take as key points? The maximum and minimum points, as well as the intersection of the curve and the x-axis, should still be taken. Their coordinates are, in order, negative pi, negative 1, negative half pi, 0, 1, half pi, 0, pi, negative 1. Now we are able to make diagrams of sine and cosine functions. Please watch this example with me. Please use the 5-point method to draw a diagram of the following function. Let's first take a look at the first function, y equals to 1 plus sine x. X belongs to the closed interval 0 to 2 pi. Which 5 key points should we take? Since we have added a unit to the value of sine x, we can take the same 5 key points as the sine function and calculate the corresponding value of sine x for each one. Then calculate the value of 1 plus sine x. Afterwards, based on the table, draw points and connect them with smooth curves to obtain the graph of this function in the closed interval of 0 to 2 pi. We compare it with the graph of the sine function in the closed interval 0 to 2 pi and find that for each x, when the horizontal axis remains unchanged, the vertical axis is increased by 1. Therefore, it is essentially obtained by shifting the graph of the sine function in the closed interval 0 to 2 pi upwards by 1 unit. Okay, let's take a look at the second function again. y is equal to negative cosine x, and x belongs to the 2 pi closed interval 0. Which list of 5 key points should we choose? Since cosine x is given the opposite number here, we can still take the same 5 special points as the cosine function. Still at the maximum point, minimum point, and 0 point. Then calculate the value of each cosine x, calculate the negative cosine x, draw points according to the table, and connect them with smooth curves. We obtained an image where y equals negative cosine x in the closed interval of 0 to 2 pi. We compare it with the graph of the cosine function in the closed interval 0 to 2 pi and find that for each x, the horizontal axis remains unchanged, while the vertical axis takes the opposite number. So essentially, it is obtained by symmetrizing the graph of the cosine function in the closed interval of 0 to 2 pi about the x-axis. Finally, let's review the content of this lesson and ask everyone to think about the following questions. How do we create sine and cosine curves? Firstly, we created a sine curve by dividing the closed interval from 0 to 2 pi into equal units and circles, using the definitions of unit circles and sine functions. Then shift the sine curve to the left by half pi units to obtain the cosine curve. Secondly, how to use the 5-point method to make diagrams of sine and cosine functions. Generally, when precision is not required, we can use the 5-point method to make a function diagram. Here, we usually take the maximum point and the intersection point between the curve and the x-axis. What are the basic methods for creating function graphs? Just like the two methods we used in this lesson for sine and cosine curves, they are the point drawing method and the image transformation method. These are also two important methods we commonly use to create function graphs. That's all for this lesson. Goodbye, everyone.